All right, good morning, everyone, and welcome to the presentation this morning. This is Dr. Rino. He's here to talk to you guys about the history of calculus and real-life applications and what you can do with calculus and lots of cool stuff.
Thank you so much. I'm. If you're wondering what's my full name, it's Ruggero Aurelio. No one can pronounce it, not even my family. So that's why we stick with Rino. In my Chinese family, my wife is Chinese, so try to ask the Chinese to pronounce the name is nightmare. And so that's why we stuck with Rino. If you have any question, you can stop me and say, "Hey, Rino, what about this?" I'm an associate professor at Massey University, Albany, so not that far from here, and basically live in the North Shore as well. And I'm a Rutherford Discovery Fellow. It's a fellowship that they give every year to 10 people in the country. And the main reason behind it is that they buy out all your teaching, so they pay you to do full-time research. And then I come and teach regardless. So I'm breaching their own policy. So I do a lot of talks about different things. And today, this is my first time talking about calculus. And we organized this talk because I was talking with Francis, and he was telling me, it's so difficult to convince students that calculus is really useful. And I agree, it's difficult because we teach it probably in the wrong way all around the world. We need to give some more meaning to the calculus, unless you are really a geek like me and you will love it regardless. So today we are going to see a bit of history, and probably you're familiar with at least one of the two guys there. Can you recognize one? Isaac Newton. Which one? The fat one or the slim one? The slim one. Who is the other one? It should be famous because it's the other father of calculus, and we are going to see why. And there is a lot of spicy story behind what happened back in the days, and fight and argument. So we are humans also. When we talk about boring stuff, we manage to complain about and fight about anything, even calculus. So I'm basically a farmer deep inside. I come from a farming family from the south of Italy, and my ticket to get out of that cycle of being a farmer over generation and a generation was physics and maths. I demonstrated myself to be good, and that's why my father said, "Okay, we'll try to send you to university, but do something useful in your life. Don't study physics or maths." That's why I did engineering instead of studying physics and astrophysics and all cool stuff. I'm gonna be a boring civil engineer. So it's the guy that gets trained to make sure that the building stands still, it doesn't fall off when there is an earthquake, build bridges, roads, and stuff like that. It sounds boring, but if you start seeing the science behind it, you start getting really excited. And eventually end up working in a construction school here in Albany, and we do a lot of advanced stuff and research. Towards the end of the presentation, I'm going to show you a bit of the crazy things we do with people. So my PhD is in fire engineering because I study quite a lot how people behave during emergency. And this is just a simple simulation that shows how I spend my time. Try to create a model that can predict human movement. And I do it as a work, and they even pay me to do this stuff. So it seems like I'm playing video games. In fact, according to my wife, I'm playing The Sims, but not the truth. I do many other things in my research, but this is really the core of what brought me out of Italy and start doing research all over the world. If you want to know more about me, just Google it, and you'll find me on Wikipedia. So I really know about calculus because in Italy, we need to study a lot of calculus in the high school. Especially the school structure is completely different. If you decide to do study in a liceo, it's one of the high school that has two major fields. You can do the science one and the classic one. And no matter what you pick, you're going to do everything regardless. So no matter I did the scientific one, I have to study philosophy, history, Italian literature, English literature. And I was really good in all the scientific part, not that good in all the humanistic part. But at least they realized I was trying hard, even with Latin, but I was really bad at it. And this is the exam, final exam that we did in 2007 when I got my diploma from high school. We were supposed to solve this calculus problem. It's basically, just to give an idea, when you end up at the end of that pathway, you need to be capable to solve something like that. That is an equivalent of what an engineering student year one is asked to complete here in New Zealand. And then we start civil engineering or any kind of engineering, and this is start becoming a joke because we start doing calculus to the next level of madness. And at the beginning, it doesn't make sense. It seems like someone woke up one day and he wanted to be mean with humanity. I invented these abstract, useless things just to make people upset and feel miserable in front of it. It's not that the reason, and we are going to see it why. So there is a lot of history before two people, they say, discover calculus. I don't think it's a discovery, it's an invention, because I see it like a tool. We don't discover. You can discover something that is already there. Calculus is our way to interpret it, to make an interpretation of the words. So that's why I don't agree in discovering something. So, but we can spend hours talking about these philosophical things. So the invention was here, but you can see there was a lot of mathematics done behind the scene. There are people like Archimedes try to break the code of how to calculate areas of really complex geometry, splitting up in triangles and do the math. And then this madness keep going until someone say, probably we should start thinking about the problem in a completely different way. And the two people that start doing it were Newton and Leibniz, the guy that he was a bit more chubby. One based in the UK, the other one based in Germany. You might think, they were the friends of calculus. Were they friends? They hated each other to the deep. And we will see it why. So, according to what we know about the history, Newton conceived the idea of calculus at the beginning. And he did it, we will see it why, because he was trying to solve a problem. But back in the day, it wasn't like here that you need to publish the results. And he was a bit mental, Newton. If you see, he wasn't like a bit nice people to be around. It was a completely genius, but really awkward and difficult to deal with because he was really egocentric. And he didn't want to put out what he invented and discovered because he didn't want to start having argument with other people. So he invented calculus and he put it in a drawer and forget about it. Probably didn't forget, but he didn't use it. Then you see that someone else had a similar idea in Germany and he published for the first time. He was the first to publish. And then there is the big argument that basically Newton said that he basically saw his original paper when he was a teenager and he copied it and he forged it and blah, blah, blah. And there were years of dispute who was in charge of the invention of the calculus. The matter was brought to the Royal Society of New Zealand, the Royal Society of UK in London, and eventually they said, Newton is the father. But there was a bit of bias that Newton was one of the main person in the Royal Society of London. So that's why the decision. Now we think that both of them have had the same idea and they are independent fathers of the calculus. So, but they were not lawyers, but there were a lot of dispute behind it. And there are a lot of books and documentary about all these things. It's beautiful to see how humans start arguing also about boring stuff. We are so beautiful. What is this? Anyone recognize that?
Is that the first principle?
First derivative. I don't know what you teach it. Basically, in Italy, you need to know this to understand what's the slope of a curve in a specific points. Yeah, it seems like a madness from a notation point of view, but it's really simple concept. And it's beautiful to see that we can go to the notes of Newton and start seeing that he didn't end up with this formulation. And by the way, you will see that this formulation wasn't invented by and proposed by Newton. It was proposed by the other guy, Leibniz. But you can see this is a real page of Newton's note that in which he started putting different polynomial curves, ax squared, bx cubed, and stuff like that. You will see that he started figuring out that there was a pattern. You can see here 5x cubed, and then you start seeing the 4e a 3. He starts changing the name of the variable because for him it was useful just to calculate areas. That was the practical side of it, and stuff like that. How did he start? He started with a pandemic. So Newton, son of a farmer, his dad died 3 months he was born. So eventually, after 3 years, his mother remarried and left him with the grandparents. And her hope for him it was to be a really good farmer. Something went wrong because the headmaster of his school realized that he was too bright to be a farmer, and he managed to convince his mother to let him study and go to Cambridge for his bachelor degree. He finished the bachelor degree, and he was really doing a lot of good things, and then pandemic struck. So Cambridge shut down for 1.5 years. He had to go back home, and he had to kill time. In my pandemic, I was trying to make cheese and start learning astronomy. He managed to invent the calculus, the gravitational law, and many other optic things within 1 year. It's called the brightest year of Isaac Newton's life. So what did you do in your pandemic? Nothing. It was just 24 years, by the way. So you are still young, so there is still hope. I'm sure that when you're 24, you're going to do something similar. And so basically invented all this beautiful stuff. You probably recognize this one. It's written in a completely different way. It's the force inertia. There are the 3 principles. It's one of the principles of dynamics. You recognize this one. There are also nice, beautiful jokes about Newton and Coulomb, because then you see the Coulomb law of interaction between electric particles, and then you see that it's pretty much the same law. And the legend says that an apple fall on his head. That's humans fabricating madness. I'm pretty sure there is a tree with apple, and they took a branch from the tree and they planted it in front of the Trinity College of London. So if you go if you go to Cambridge, you will see that in front of the Trinity College, there is the son of the tree, the original tree of the apple. And the beautiful things about what he did, it was like to figure it out that the principle that an object is dropping off and the moon is not dropping off on us is exactly the same law. So why spend so much time? Because we didn't have the tools to understand why the planets were orbiting the sun in a certain way. So we didn't have the math. He created the math to solve a real problem. He didn't woke up and think, like, let me create something useless that in 300 years a bunch of kids are gonna hate me for. It's not that the case. He was trying to solve a really big problem. And one of the most important books of the history of science is this one, Principia o Mathematica, that was written in a rush because Leibniz published his calculus, and Newton was like, hey, wait a second, 30 years ago I had the similar idea I never published before. Let me put everything together. So this book has calculus, gravitational law, and the 3 principles of dynamics in one book. History changed from there. Scientific history. By using that, for the first time in the history, we could justify and explain from a mathematical point of view why planets were orbiting in a certain way. And that tool, it was so powerful that other astronomers start making calculation, and they start seeing Uranus and say, wait a minute, it doesn't move really as it should. There should be something missing here, probably another planet. They did the math, they managed using calculus to figure it out. We need to point the telescope over there and discover that there was another planet there. So it was the first planet discovered because of calculus. And then we start doing the same game and it took other couple of 100 years to figure it out what was the matter. We start observing Mercury, and they start observing Mercury. It's like the orbit doesn't make any sense. It doesn't follow the prediction of the model that we have of the universe. There must be another planet, and they start making up names of another planets, and we never figured out what was wrong with Mercury. And you'll see there is another figure that comes in the picture that solved the problem. You know what was it? It's really famous scientist, probably the most famous scientist of the last century. He didn't go much to a hairdresser. Yeah, that's the guy, and we'll see why he solved the puzzle. Another thing we need to be grateful for Newton, telescopes. This is the version of telescope was used by Galileo. By the way, he didn't invent the telescope. He took the idea from a Dutch guy and improved it much better. And then he thought, let's try to point it up to the sky. And then history changed. He started figuring out that the moon is not a nice marble ball. He started seeing that Venus was orbiting the sun and start figuring out, wait a second, it's not the Earth in the center, it's something else. Creating a telescope like this, or buying a telescope like this today is super expensive. Why? You need lenses. They are super expensive to fabricate, especially if you want to go bigger. Then Newton say, hey, let's wait a second, we can use mirrors. If you just bend a bit the mirror in the right shape, it's a parabolic shape, by the way, then we can do the same magic. You can get something much bigger in terms of size of diameter of a telescope with a mirror, and it costs 1/10 or even less. The only difference with telescope mirrors is not like the mirror that you have at home. In the mirror you have at home, if you put your finger, you touch the glass, and the coating that is reflecting is on the other side. For the telescope, it's on the other way around. So if you have a telescope, never touch the mirror. You can ruin the coating with your hands. And I know quite a lot about it because, as I said, in COVID, I started doing astronomy, and then I fell out the black and deep hole of the astronomy. So I do a lot of fixing of telescope, buy them, and sometimes even doing classes about how to use astronomy. So if you go to my Google channel, you will find this video about the basic of astronomy, or you can do it at home with the really cheap stuff. Let's go back to calculus. The two fathers. So you can see that we own Leibniz, the formalism. In this case, Leibniz was like less trying to solve a problem. It was just trying to solve a problem of how to calculate area below a curve. So that's why you start seeing something that starts coming from Latin, summa, means sum. So that's why the shape of this is like that. And then differential, difference. So also the D of differential comes from something. It's not that someone wake up and say, oh, let's call it D. It's something like that. Instead, Newton had a completely different approach because he was trying to crack the problem of gravitational law. So that's why for him, everything was about the law of movement. And I think that is really useful to learn calculus, merging it with physics. Because if you start applying a concept about the first derivative, second derivative, and then you start seeing that this is speed, this is acceleration, it start becoming easier to digest. But mathematicians don't do it, even in Italy. Especially when they teach engineering students. They really like to make us feel miserable. How can we apply calculus? Any idea? In real life, where do we use it? Say it again?
Architecture.
Architecture, yeah, of course, I'm here. Any other idea?
The spread of diseases.
Spread of diseases, we can do mathematical model on that using calculus. Any other things? So the answer is everything. We can use everything in everywhere to do everything. Thermodynamics. We use engines, and they've been like one of the main things that have been helping us to develop as a society. Forget about thermodynamics if we didn't have calculus, and try to figure it out the efficient of a steam engine, combustion engine, and we'll see also for electric engine, but it's not thermodynamic, it's something else. This is one of, I'm putting here a bit of famous equation around taken from different fields that they change the words. First, industrial revolution. Thank you, Newton and Leibniz. Maxwell equation. Telecommunication is based on that. If we can talk to someone else, if we can play with lights, if we can play with anything about electric and magnetism, this is the equation that you need to learn. And it's not simple calculus because it's calculus to the next level of madness. So if you think that what you're doing is difficult, don't feel worried. There is always different layers of madness in how you can explain nature. And if you like to watch cars, or if you like to do sport, and you want to win the Olympics, you can do a lot of research about about using Navier-Stokes and about fluid dynamics. So it's the law that we use to make sure that a flight won't fall off. And this is an example in my field about how fire and smoke can spread in a house. We can use it to predict the turbulence of a cyclist, of a car, and make it more efficient and win the F1 competition or motorbike competition. We can split up the problem in small cells, apply simple. It depends which level you are of calculus, and then we can run through really beast of computer simulation. Back in the day, it was impossible to run this on any computer. Now it can be run on a laptop and most surely also on a smartphone. But when you run a lot of this equation, million of time, you will see that everything starts boiling and you can start cooking an egg on your computer. And I burned a couple of computers using a CFD, computational fluid dynamics on them, and never told my mother. Anyway, this is the other equation that changed the world. I don't know why they say that the most famous equation of Einstein is E equal mc squared. Yeah, it is one of the two famous, but this is where it cracked everything. General relativity. So you remember that we couldn't figure it out why Mercury was moving in a really funny way. The equation of Newton are not that good when there is a massive object like the sun and a small object like Mercury. It's not good enough to make any prediction on that. You start seeing that the math start breaking down. We need to use something more advanced. Einstein managed to find the solution. Curvature of time-space. Space-time, sorry, I'm swapping. I'm a bit dyslexic and I swap things in my brain. So this is just a simulation showing how this works for the Earth, but the best way to simulate and show a simulation of time-space space-time bending is through this one, because there are 4 dimensions and we need to see the other dimension with color. And of course, black holes and other things that we couldn't even figure it out, they were real. Why? Because Einstein proposed this equation at the beginning of the last century, and then there was a guy in Germany in the middle of a war, World War I. It was one really good mathematician that was helping doing the calculation of how to shoot with the cannons. He received a manuscript of Einstein and he started figuring it out. Let me play a bit and simplify it and something like that. And said, wait a second, what is this stuff? He had the first solution that showed there might be a black hole if you have too much mass concentrated in a spot. You start calling it singularity. And we still don't have any clue on the math that we need to use, because close to infinity, calculus breaks down. So we know already that we can't rely on even the equation of Einstein to explain how a black hole is working. But we can do really good prediction about the event horizon, the place where the light, anything else can come back. It took us another 30, 40 years to figure it out. the black hole are not just a mathematical solution, they are real. And it was through putting telescope towards the core of our Milky Way, Sagittarius A, we start seeing that the stars were moving or orbitating something that wasn't visible. And the guy that made this discovery, just observing the trajectory of the stars, they didn't say, we discovered a black hole. It might be a black hole. They got a Nobel Prize out of that, of course. And now we are putting radio telescope and try to create things that look a bit like this. This is a simulation, but you have seen the picture of a black hole using radio telescope and a lot of simulation. There were so many people involved. Schrödinger equation. If you have watched the Big Bang Theory, at least you have heard about Sheldon talking to Penny about the Schrödinger cat that is in superposition, can be dead and alive at the same time. Have you ever heard about it? So it's quantum physics. And when we go straight to the other things, on the other sides of the universe, you will see that matter behave in a way that doesn't make any sense. It doesn't seem to follow deterministic law, but it starts following probabilistic law. And Einstein died without accepting it. There was so much dispute also there between Bohr and Einstein challenging each other. And we still don't have any clue about how to interpret quantum physics. We know that this equation works, but we don't know why. From a philosophical point of view, there are different interpretations. The Copenhagen interpretation, there are many others. And sometimes I spend time teasing a professor at Massey University because he's one of the physicists, the most bright physicist in New Zealand. If there would be ever a Nobel Prize in physics from New Zealand, he will be one of them. And you go to his room, he has this kind of odd sign of the wave function, and I ask him if his cat is dead or alive, like the Schrödinger one. Let's go and talk about practical things. Come on, you all did this when you were kids, or probably you're still pretending to do it to help your brother. If you don't put water in the sandcastle, does it stand? Why? So we can use an empirical approach and say, okay, let's start putting a bit of humidity or water and see if it works. Let's put too much water, it doesn't work, and then you start figuring out there is a nice balance behind. Now, if I go to my father, he might tell you, yeah, you need to put enough water, but you won't have the mathematical means to explain why it's happening. If we go and see what's happening to the soil, and then we start knowing what is the property of water's tension, of water, like any liquid has a tension. And by the way, it's nice to see that water has the tension that goes in one concavity, mercury completely the opposite. It's the same reason when you put a straw in water, you start seeing that it's going up. Water tension and calculus can help you explaining that if you have a bit of water here, there are forces going up. And if you do the integration, you can even calculate the force that hold together the sand. And of course, if you put too much water, then there is no any longer air and water and surface tension. So there will be, the sandcastle will melt down. It's because you lose the magic of using that stuff. So did I convince you that calculus at least will help you to get your castle standing? But of course, we do much more advanced things. We can afford for building that, let's try this and see if it stands. And then good luck with that. And that was the way we were building cathedrals back in the day, without any equation, a bit of experience, and people, it might stand. And sometimes people were crushed under those, yeah, it might work. Health and safety, 0, and it was like just empirical idea and see, let's hope that it's gonna work. But you do, I build it. I'm the architect, I need to stand away from it. Now we have the tools because of mechanics and mechanics of material that help us to make really advanced calculation that allow us to make any prediction if something is gonna stand even in an earthquake. And those are the equations. So you can see that this is just, they're all differential stuff. This is basically the sign of deformation, elastic deformation, and this sigma is the tension. It looks like really complex, but if we go and see just one of these, you will see that this is the relationship we were talking about. And we have the tools in Massey in which we start pulling, and you see that you start getting a chart like that until the steel snap. And steel is a relatively good material in which you can make the assumption, when you don't stress it too much, to be elastic. Concrete, it can be trickier, because in one direction it can be elastic, on the other direction it doesn't. And using this equation, differential equation, you can even start thinking about crazy material. Imagine a material that you push. This is a positive sign. That means we push, so that means that the object gets smaller. Imagine material with the negative E. You push and it became polar. It will be nice for me, at least. Or we have the other parameter, the Poisson ratio. You push and then it became wider. Imagine material that you push and you lose weight. It will be nice also for me. Can quit gym. And by using this equation, we can explain a lot of material from really simple cubes. And this is something that we do in construction. We need to take a sample of concrete before we do the pouring for foundation or whatever we are using, and check that the concrete has good capabilities. And if we use the calculus equation and we start splitting the material in small and small cubes, and you start doing a simulation, that's what the simulation is telling you. If you press something, then you start seeing here that the particles wants to run away from it. And if we start doing it even with a sponge, you will see that if I start meshing it, oops, this is second deformation. If we start pressing enough, you will see that it will start expanding one direction. And we'll see what we are going to use this. Looks like calculus, right? If we do it in reality, so concrete, do you think it's going to be capable to be pulled apart? Yes, no? Concrete is really good for compression, really bad if you try to pull it. So according to this model, here the material is going to fail. So that's the prediction of the model, and this is reality. You see that it's cracking exactly where the model is predicting. So that means that the model is capable to predict reality. And this is for a really simple things. And we can apply for a whole building with calculus. And that's how we waste 5 years of our life at university as a civil engineer to make fun, really accurate prediction of this stuff. So this is a beam. And I brought a light version of it. In this case, is a good example of elastic material. It comes back. Plastic material will be like I push it and it stay there, or it comes back slightly but not in the same position. This is a good way to show that this is kind of elastic. So, yeah, that's the good one. Where do you think you're gonna have compression? On the top, on the bottom? So this is the diagram of the deformation of the beam. If we slice it, you will see that there is a part that is elongating and a part that is compressing. Where is the part under compression? Top. And I wish I had chocolate to give to you, but I forgot it. And you will see, if we have a beam and we start squeezing, and you start measuring the length here, you will see that this line is going to become shorter, 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 while this one is becoming longer, 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 longer. So you remember what I told you about concrete? And concrete doesn't like to be pulled apart. So if we push and push and push, where we are going to observe cracks? On the bottom. And that's what you will observe because it's not a plastic material. Wood, slightly different because in the wood you can even pull it. And I'm Italian. Let's talk about spaghetti. What happens if you pull a spaghetti, if you bend a spaghetti? Spaghetto is the singular in Italian of spaghetti. Would you get a crack or multiple crack? There are people doing math to figure it out why we don't never capable to split a spaghetti in two and don't break them before cooking. Otherwise, it's insulting my culture. So then someone came out at the beginning of the last century saying, what if we start putting concrete and a bit of steel? We put the steel where we need to handle the extension, and we put the concrete to handle the compression. This is how reinforced concrete works. Even if you push and you crack the concrete, there will be still holding everything together. And if you want to do the calculation, you will see that it's not any longer a triangle, so you can cheat and use a bit of trigonometry to calculate the forces. You need to start using calculus to make a calculation of what's the compression force there and figure it out what's the tension force on the steel. No way around. I oversimplify, but we used to do math to figure it out and explain all the equations that we use. Now, this depends on the material, and this depends also on the feature of the beam. So if I put a beam in this way, it's not going to be really effective. Let's put something heavy and useless. Couple of books. You see that this is the deformation. We can use exactly the same material in a different shape. The property of the material has changed. Of the structure is changed, the reaction. And you can see it's unstable both on the other side. So you need better if you put something, if you build something like that. That's the beam. It's not that by chance they put in that way. Exactly the same material, non-performing. So you see, engineers are not completely nuts. Well, talk to their wife. I have different opinion. Husband, well, you're an engineer as well. Things start becoming crazy because it's easy to use calculus when things are statics. If I start putting a bit of earthquake style vibration, then you need to start using really complicated equation to take in account what's the vibration of the objects, what's the vibration of the full building. And we have mathematical tools that are capable to do this with extremely precise estimation. And we build codes and regulation based on that. Bridges. Bridges are really beautiful because you can see where the tension is going. This is a suspended bridge, like the Golden Gate Bridge. And you can see that the force needs to go up and then it needs to go this way. So you can clearly see all things to, of course, move in a bridge, in a static situation. Of course, on the bridge, cars and vehicles. So all these things became more dynamics and advanced, and we have all the equation to calculate that. They might give you nightmares, but we still have the equation and simulation capability to predict bridges. We use it a lot. Let me check the time. I don't want to. We're getting close to the end. Otherwise, they're gonna shoot me down. Foundation. I forgot to tell you something really beautiful. I mean, beautiful for an engineer. For you, it might be something. Okay. Why the steel doesn't rust? It sounds like a joke. Why the steel doesn't rust in the concrete blocks?
No oxygen.
No
Oxygen.
No, there is oxygen. It can penetrate. Come on. It's a symbiotic beauty of engineering.
There's no moisture.
Oh no.
Really.
still the moisture can get in, even if we put a bit of water.
Rust.
No, it's the pH. If you get the concrete and you analyze, the characteristic of the concrete is to be slightly alkaline. Perfect for metal not to rust. So you see that sometimes then there is rust within beams. It's because there is an alteration of the concrete. Water penetrates, it takes away the carbon, so the material start becoming more and more acid. And that's why then the concrete, the steel starts rusting and then expanded because the rust is occupied, the metal, rusted metal occupy more volume, so it's not, and then you see rusted concrete. Otherwise, perfect symbiotic, from an engineering point of view, relationship. Foundation, same. Most of the time we use this foundation for this building. I'm pretty sure we are using this foundation. And you need to calculate the interaction between the soil and the building, all done with calculus. To build high-rise building, you need to have a really deep foundation. That's what happened in the CBD. You can go and put the post directly on the rock, or you can even have it in a muddy situation. So you can see here that there are time forces, and then you need to do an integration around the circle and then going up. And of course, that tension is not constant. It would have been twice easy. Then otherwise we could just do simple equation and math. We have models that predict all these kind of features of the soil, and we can do prediction. That's why we don't build things as like, oh, it's falling off. Sometimes we do it, like even Italians, you see with the Pisa Tower. We didn't have the math to figure it out. And that's the results. But at least now we are doing a lot of good money out of it, or out of our mistake. Dam. It is one of the most famous dams in the world, Hoover Dam. I tell my wife, European, Italian, French, really, and a bit of English did a really good engineering. Americans brought it to the next level because they need to build infrastructure that we don't need in Europe. So also in this case, if you want to calculate the dam, you can have, this is the diagram of the pressure of the water. So you need to figure it out what is the total force applied to the dam. So because then you need to build something that it can hold and withstand that force. But then there is pressure from the bottom. There is infiltration in the, it's a nightmare to build a dam, but it can be fun. And we have all the equation about all the hydraulic behind it. We have all the equation about all the geotechnical. We have all the equation about all the material, how it withstand these pressures. And they are all based on calculus. To finish, we use it calculus also to understand human behavior. This is one of the papers I wrote during my PhD. We simulate people during emergency. Imagine there is an emergency here, and an alarm starts going off. I can tell you that you won't start evacuating straight away. You won't. It will take time to try to figure it out what others do, what's happening. And what we do is to model that as a thermometer. You have a risk perception inside, and when you feel like the risk is too high, oh, okay, I need to do something about it. So this was the concept that I didn't invent it. It was based on observation of the evacuation of the World Trade Center. Before the Twin Tower collapsed, there were many people that managed to evacuate, and there were huge investigation. And I had one of my colleagues did all the analysis of this interview for her PhD. And I've been working on NIST, where the main investigation about the collapse and the evacuation carried out in close to Washington, D.C. I've been working there. And one of the guys there developed this fancy differential equation to explain how risk perception change based on what people observe and experience. And this is just one of my solutions for it, to show that there is, if you receive different level of cues, then the risk keep going up, up, and up. And you can do simulation using that to predict if there is an emergency in this building, how long it will take for people to start answering, the responses start getting out. Calculus. But We can even figure it out with calculus why people don't bump into their door or in the walls close to the door. This is a model we just developed 2 years ago, and it's based. I developed a model that was similar, and then I started talking with a friend of mine, a priest that has a degree in a bachelor degree in mathematics, and then he did a PhD in theology, and then he became a priest. But he was telling me, have you considered about parametric equation to explain that? That means, have you considered that people probably don't try to go straight away to the exit, and they try to aim something close in front of the exit, and as they are approaching the exit, that goal starts shifting behind the exit. And by using this simple concept and a bit of math, we managed to create this beautiful equation that is capable to explain why people, if they are here, they don't start scratching against the wall to get out of the exit, but instead they try to get away from the wall and then bend and get outside of a door. I think this is the most beautiful piece of evidence of how people get out of the exit, but my colleagues don't like it and they don't cite it. And we managed to do also simulation. And demonstrate this is our model to show that our model is much closer to what we actually observe when we have a crowd try to get out of an exit. So that's from me. Thank you so much, and thank you to Newton and Leibniz. Thank you.
So I had a very good time listening to this. I think this is the best Friday hour I've spent in quite a while. No offense. So I want to say thank you. Thank you for coming, talking to us. I think some of these guys also enjoyed it. Since we're level 3 going out next year, we really needed to know this. So I feel more confident with going.
It's not a waste of time. It's a good waste of time. Let's put it in this way.
Yeah. So guys, one more time.